On the topics of yesterday, really looking at decarbonizing shipping and how we should go about doing that. So I will a little bit discuss the topic, but I will also give a little bit of suggestion what are the right solutions. So, is this, yeah, okay, good. So if we are looking, of course, what is driving the industry today, it's climate change. Just a couple of years ago, the big topics were still SOx and NOx emissions in the marine industry. But now everyone is focusing on greenhouse gas emissions. And that is right so, because we need to do something with climate change. And a little bit. Not working? Okay, now we've jumped a lot. Okay, so IMO has recognized this. We all know that they have put in targets for emission reduction, and they are talking about a 50% reduction by 2050. Some people think this is quite ambitious and hard to achieve. Other people think it's way too little, way too late. They have put in some measures. What can be said about those measures? They are good, but they will not get us to the 50% reduction. Additional regulations or other market instruments are needed to achieve this. But fundamentally, this will basically lead to a fuel transition. If you look at what we can do to reduce greenhouse gas emission from shipping, we like to approach it with this triangle. First, we should really try to avoid consuming energy. So minimize the energy demand on board the vessel. And there's a lot of things we can do there. Everything from slowing down, basically operating the vessel in a more efficient way, and so on. Then we should select a clean energy source. Be that a different fuel or sun or wind or something like this. And then we should convert this clean fuel or energy source in the most efficient way to the type of power we need on board the vessel. Traditionally, in the industry, we have focused on two of those corners, energy reduction and efficiency, but these will not get us to the target, so we need to look much more into the clean energy sources as well. However, we should not forget the other two corners, because whatever these new energy sources are, they will most likely be more expensive, so the less we need of them, the better. But we will need new energy sources, and this will lead to a new era in shipping. And this is categorized by the fuel transition when we go to low carbon fuels. However, there is uncertainties around this. First, we don't really have an ideal fuel. There is not a silver bullet, one fuel that fits all parts of shipping. The other uncertainty is the time frame. As mentioned, the regulations that will drive through the transition is not yet in place. We don't exactly know when this will happen, when this market instrument or regulation will come into force. So the time frame of this transition is open. So there is uncertainty. And if you're looking at how far we have come, we can say that the pickup, these are all the ships today that are using alternative fuels or basically are on order. As you can see, there are not that many, and most of them are LNG or hybrid vessels. Very few vessels so far with really what I would consider alternative fuels. So the positive thing is its upward trend. It is a growing market. So what are these low carbon fuels that we should go for? Well, you can, there are many options, and we heard a lot of them yesterday. It's hydrogen, methane, ammonia, methanol, and other things. But you should really look at these fuels also from the point how they are produced, because the same fuel can be made in different ways, and the sustainability depends greatly on how it's done. And you can say there are three main pathways to low carbon fuel. We have fossil fuels with carbon capture. It has potential. Some people do think it might not really be that sustainable, so let's see. So many people do believe the more likely fuels are either renewable electricity or biofuels. Biofuels, on that side we have HVO or biodiesel, biogas, or biomethanol really as the main options. The problem with that is really how much of these fuels can be produced. Is there enough biosource to make this fuel? And no, there is not. But they will definitely play a wide part. And then we have the renewable electricity. And these are the power-to-X fuels or e-fuels, many names for the same thing. And here is basically when you create hydrogen, and then you can convert it to another energy carrier or use hydrogen on board the vessel. But when we compare these fuels, it's really important that we look at the total life cycle emissions. So not only look at what comes out of the funnel of the vessel, but actually the total production chain from the source where we get the energy all the way until it's delivered on board. So we need to look at the entire emission path. And this is shown in this graph. So here in this graph, dark blue bar is the emission from the well to tank. And then you have the tank to wake emission as the light blue bar. And of course, the larger the bar is, the more dirty the fuel is. And what we can see from this is that when we look at fuels, it do play a big part how it's produced, as mentioned earlier. For example, if you look at hydrogen there, if you take the hydrogen that's available out there today, the gray hydrogen, has a very big dark blue bar. All the emissions coming from the well to tank part, but it's very high emissions. So we actually make the world a worse place by using this type of hydrogen. So if you want to be environmentally friendly, you need to go for green hydrogen produced from renewable electricity. And that's clean. Other options, you see similar trends for methane and methanol and ammonia. It depends greatly on how it's produced. So really the low carbon options are the bio and the renewable electricity alternatives on this chart. What you see there is also that there's this dotted line for some of these. And that means that it's basically a renewable fuel in the sense there will be CO2 emission coming out of the funnel, but it's renewable, so it's carbon neutral. So there are many good options there, but we need to see how the fuel is produced. Of course, when we select fuel for a ship, it's not only about looking at emissions. We also need to look how practical it is to bring on board. And I just highlighted some of the features of fuels in this graph. One aspect that is quite challenging is the space demand, especially if you look for hydrogen. And I've indicated here in this chart that hydrogen requires a space somewhere between 8 to 26 times that of diesel. This depends greatly if it's liquefied hydrogen or compressed and how it's stored. But if you would take just a container of hydrogen and put it on the vessel, it's about 26 times the space demand compared to diesel. And that's not very easy as a naval architect to fit on board a vessel. But also, I mean, ammonia, methanol, and methane all require more space than traditional diesel. Other aspect is safety. And we heard yesterday, there was already some discussion about this. Hydrogen, highly explosive, and it likes to leak. It's very hard to contain the fuel and have it 100% leak-free. So you need good safety concepts around that. Ammonia, methanol, both toxic. And that puts a challenge on what type of ships you can use them on, and so on. So there are many things to consider when you look at this. Another thing to consider is really the energy efficiency of using this fuel. This is just an example comparing if we have this clean electric power coming from wind power or solar, and if we want to use it in a ship, the best way to do that is with a battery. Because then about 80% of this clean energy will actually go into the propeller. But if we go down the path of hydrogen, only about, well, a little bit more than 20% will be left for the propeller. So it's a highly inefficient way of using our clean energy. Actually, you could argue that if we want to reduce emissions, we should not make these kind of power-to-X fuels for ships before we replaced all coal power plants on land. However, of course, our industry needs to do something, so we cannot just sit there and say that the other guys should do something. But it is something to remember, the efficiency of producing these fuels. Similar chart you can make for green ammonia. So you lose a lot of energy when you do the electrolysis process, and then when you do the further conversion. Every time you convert, you lose something. The nice thing with ammonia compared to hydrogen is, of course, that you can run it in an internal combustion engine. It's easier to store and so on. So you get the same efficiency or better with green ammonia, and it's easier to use. So it might be a more logical choice. Of course, the next thing to consider is cost. And I don't have the price of what all fuels will be in the future. But this chart I just made because there's a lot of discussion saying that, well, these green fuels will become very cheap when we get the mass production going. However, I don't really believe that. First of all, they are all made from renewable electricity, these fuels, and this hydrogen. And this renewable electricity has a value. I mean, we will need a whole lot more renewable electricity in the world for the next coming 30 years. So this electric power will come at a cost. Why would anyone give it for free to make? So you can just take the market value or the cost of renewable electricity and just calculate that the minimum price of hydrogen or the energy price content in the hydrogen has a price that is already much higher than diesel or LNG today. So I put 3 options there, depending on what you assume that electricity will cost. Then you need an electrolyzing plant that comes with a capital cost that you need to pay off, and you need to maintain it and so on. And that adds a little bit more cost to this. Of course, this is an area that can improve. And then you need to distribute it. So basically, I'm estimating that hydrogen will probably, if we start with a price of 5 cents per kilowatt hour, it will probably cost around 140 something euro per megawatt hour. And if you compare that to diesel, okay, before Ukraine crisis, that cost 44. So it will be multiple times more expensive. Some people then argue, okay, what I get the economy of scale. Really what that will impact is the production process. So yeah, I can a little bit lower it. Then someone says, well, I have this fantastic free energy at nighttime when the wind is blowing and no one consumes my wind power. What happens then? Well, yes, you can lower the electrical cost, but then you cannot run your electrolysis plant all the time. That will only run part-time, say 25% of the time. And then that capital cost goes up. So there is no free or very cheap hydrogen or other power-to-X fuels to be expected. So we need to assume that this cost will be high. That's the point here. On the other hand, shipping can afford it, or the world can afford it. If you look at container rates today, they are about 8 to 9 times higher than they were 2 years ago. And trade is still flowing. Customers are still buying containers, shipment. And that's a much bigger increase than what this fuel will ever mean for shipping. So now I discussed a lot of different aspects. So what do I believe? This is my chart. This is what I believe will be the likely fuels for different ship types. And as you see, the likely fuel depends greatly on what type of ship we talk. So for example, if we talk about a tug or a road ferry, I think it's a battery, maybe a little bit of hydrogen or HVO. Whereas if we go to the mainstream shipping, bulkers, containers, tankers, it's green ammonia, synthetic methane, or biomethanol. And these are, of course, these tankers and bulkers and containers, that is 80% of your emissions from shipping. So that is really the bulk, the main things. But what we can see here is that there is not one silver bullet that would fit all ships. And at the same time, we see that it's greatly depending on what type of ship we are using. For example, passenger vessel, I would not put ammonia on because it's so toxic. So it comes out different. So it's really there. And the other thing you can see here is that it's very few ships that I believe that will use hydrogen as such. It's really locally operated vessels where batteries might not be, you don't have enough energy in the battery, or inland waterway vessels. But otherwise, hydrogen as an energy carrier is not the fuel for shipping. unlike what some said yesterday. That will not go on board the big vessels. We will use other energy carriers then. So, having said that, still, as a company, we are looking into hydrogen. We are working with that. We have great examples. We have the High Seas 3 EU project. We just developed a solution for how to power a ferry with hydrogen and fuel cells and batteries, and really learn how to integrate and optimize all that. We have the next ship in the project in the line, High Ship, which is a bigger RoRo ship that will use also hydrogen combined with fuel cells and the batteries. And we have battery-powered vessels. So there's a lot of ongoing, and there is some ammonia vessel concept project as well missing here that we are doing. So this just shows kind of a test facility where we are testing, or where we tested hydrogen with fuel cells and all this. Full scale, full machinery, run in realistic conditions, but on land. So we are ready. We know how to do it. And so on. And of course, batteries is a good solution. I mean, there is a lot of ships where that is applying hybrids, but also ships that are going for pure battery. And especially small vessels like tugs, ferries, and these things. But question is here, how big ships can you go with batteries? What's the limit? I showed that battery is the best way of using renewable electricity. So how far can you stretch it? And for that, I made this case study. This is a RoRo vessel, 1,500 lane meters, so already a quite big cargo vessel. Can that be economical on electric power? So what we did, we compared normal diesel ship doing 20 knots with hydrogen and a battery solution. And what we said from the beginning is we're going to lower the speed to make it feasible. So we looked at 16 and 9 knots. And then we looked at different length of routes, because that, of course, impacts a lot the feasibility. And the end result is shown in this graph. So this is the total transport cost for that RoRo vessel. So this is assuming, accounting for the lower speed. So this is actually how much does it actually cost to transport one trailer. And the 100% bar, that's the diesel vessel. And what we see is that the hydrogen and the biofuel vessel will be more expensive. They are higher up. But the interesting thing is that the battery vessels at 9 and 16 knot is actually on short routes cheaper than diesel. And that is today. So basically, I could go to a ship owner today, build him a battery vessel, transporting cargo at 0 emission at lower cost than what he could do with diesel. So that's a no-brainer. Win-win. 0 emission, lower cost. But it works only on short routes. So we can go up to 100 nautical miles. On the other hand, in Europe, there are quite a lot of routes under 100 nautical miles. English Channel, Gulf of Finland, Scandinavia to mainland Europe. A lot of RoRo routes there. So there's a big potential. Hint for all ship owners here, if you want to make money and be green, this is the solution. But it do require that we think differently. We need to make a better ship. We need to lower the speed, look at the design, and really come up with new concepts how to do it. And we have one solution here, but there are many other options to do it. Okay, that was a short route. What if I have a cargo vessel and I want to go far? So for that, I've done a case study for a container vessel here, a feeder 2,000 TEU. What is the right solution there? Because from the outset, we can say battery will not work if you're going to go thousands of nautical miles. And this is really the question a lot of ship owners coming to us with today. Well, we know this fuel transition is coming, but we don't know when. Which fuel should we select? We don't know. We know the customers will demand more green transport in the future, but still they are not paying that much extra. And there's other new technology coming. So what should I buy? I want to buy ships, but how do I ensure that my investment will still be attractive in 10 years' time? And that is what we really looked at. And we make these kind of graphs for a lot of ship owners today, where we plot different alternatives. And on the horizontal axis, you have the the emissions. So the further to the right you are, the cleaner the vessel is. And on the vertical axis, you have the cost. And this is total cost again. So this is investment cost, operating cost, all the crewing, everything included in that. And 100%, that's the reference vessel. That's your normal diesel-fueled container vessel. And what we see here is that putting on LNG, I can reduce the emissions a little bit more than 10%. Not big, but slight there. I know there are some arguments of methane slip, and so that is accounted for here, because we go two-stroke, high pressure, so there is not so much methane slip. But then if you want to make it better, I can put in a more efficient machinery with a large PTO, different things. It becomes better. And then I put some flattener rotors on it, wind power, and I get a little bit up to a 30% reduction. And this is nice, because actually, it's lower down, so it's cheaper. So this is a no-brainer. This is competitive today. It's actually better than your standard vessel today, and you reduce emissions 30%. But of course, in the long run, 30% emission reduction will not be enough. So what should I do then? I can start blending in a little bit of hydrogen in the vessel. Not a good idea. Don't blend hydrogen and other fuels. You complicate the vessel, and the improvement is quite marginal. By biogas. Today, that's the best option. And some ship owners are doing that. Very big emission reduction and not that big an increase in cost. So if you want fuel cells, hydrogen, ridiculously expensive. Not worth, not going to fly. And you see full battery also, not going to fly. So really what I'm saying, start with LNG, and you can run biogas and with the same ship today. So you can do your 80% emission reduction from start. And then prepare the ship for ammonia and methanol. Then you are covered. You have a low carbon ship, and it's competitive, no extra cost today. And how we do it is this. We build a ship. Of course, we make it digitally advanced. We put all the vessel insight and all those apps on board that you can upgrade it digitally. We prepare it for wind power. But what we do is we put in LNG tanks that are ammonia ready. Because that means that from the beginning, we can run biogas, we can run synthetic methane and normal fossil LNG. We can run diesel and HVO. So we basically have 5 fuels, 3 of them are low carbon. And then with a small conversion, I can get the 4th low carbon option, ammonia, in there. Of course, that requires that we have an engine that can be converted. So we put in this case, it's the MAN, dual fuel engine, high pressure. And then we put in a big PTO and a CP propeller. CP propeller so that we can add wind if we need and want. If you have wind power, you want a CP propeller in the vessel and not a fixed pitch. And then a big PTO. But we make that PTO as a PTI, so a motor as well, because that means that we can put in batteries and do zero emission entry and exit out of port on pure electric power. That might be required in some areas in the future. So again, we prepare the vessel with low cost, and then if it's needed, we have the space reservation. And then, of course, we need space reservation for additional tanks as well, if we're going to go ammonia, because ammonia requires more space on board the vessel than LNG. So altogether, a cost-competitive vessel from the beginning that can evolve with time. This is just showing when you should do the switch. How big cost on CO2 should there be, carbon tax or emission trading? And it's around 150 euro per ton where the transition for this vessel makes sense. So as you see, the carbon tax needs to be quite high before we actually start switching fuel. And no matter how high the tax is, it will never make sense to go with hydrogen. It's just ridiculously expensive. Okay. Since there was a lot of discussion yesterday about this offshore wind, I added a similar chart for a SOV vessel. So again, what is the right fuel there? Because it's a little bit different outcome. And I will not go through all the things, but what we can see is that really the best option is to go with battery and offshore charging. A vessel with the battery capacity to run one day and charge in the night offers you the best economic performance versus emission trade savings. So that is really what I would recommend. Again, forget the hydrogen, forget the expensive fuels, and so on. HVO with a hybrid, quite good as well, if you don't have access to the offshore charging infrastructure. But that is coming. So with that, I need to start to round up. So what did we conclude? Well, electrification, yes. If you can make a ship work on batteries, that is the best solution. But do look at new designs, lower speeds, how to operate it, and seek new novel solutions. But batteries is definitely there. If you want to be future-proof, I think the solution there, what should you buy? It's something that you can alter and evolve with time. So start with LNG, but prepare it for other fuels. Put in the battery readiness, put in the readiness for wind, or install the wind from the beginning, wind power, all this. But do aim for best efficiency, because whatever you do, minimizing your energy reduction is key to keeping the cost down. And then really, the fuel transition, what should you do? Well, my recommendation is keep multiple options open. Don't lock yourself to just one of these fuels. So go with different alternatives that make the ship capable of switching, because we don't know what the future price of these fuels will be. So I would recommend that you make a fuel-ready vessel with different options. And probably LNG is a good starting point, because then you can run biogas or synthetic methane directly, and then easily convert it also to ammonia if you make the right preparations for it. So with that, I would like to thank you for your attention and hope for some good discussions today.